Hey there. Okay, so this is our summary video, and I just am going to basically scroll through the terms. I've listed a few terms from the backs of each chapter that you might be interested in looking into, and they will help you to answer the suggested questions, and also hopefully this will encapsulate everything that we've talked about in the previous three videos. Okay. So, the first thing I need to tell you is that those three videos were not divided by chapter, they were divided by concepts. And so, what I'm going to do now is draw the concepts that we learned in the videos to connect to the concepts that you'll be reading about in the chapters so that you can see them all as the same thing. Okay, so let's begin with Chapter 9 terms. The first term that I've chosen for Chapter 9 is chemical reaction. Now, you've probably already seen this. We definitely did some of that in lab. It's important for you to understand the difference between a physical exchange and a chemical exchange. So a chemical reaction is very specific in that it means that bonds were broken or formed. So you don't get chemical reactions if, for instance, you put something in water that's not soluble in the water, so it doesn't dissolve in the water. That's not a chemical reaction. Um, if you mix two items together really, really, really well, and they don't form a new chemical, they don't form a new substance, then you have not had a chemical reaction. Uh, it's important also to realize that physical reactions can be in gases or in liquids. And so, for instance, water evaporating off of the surface of a pool of water and into the air forms water vapor. But if the water vapor is just wandering around as water molecules, then it hasn't formed a chemical reaction at all. It's just a physical action. But if it actually starts to interact with the oxygen in the air or interact with the nitrogen in the air, you then have a chemical reaction. So that's really important for you to understand in terms of chemical reaction. Bonds have to be broken or formed, or both. It could be either. It can be and or. Okay. Next, the covalent bond. Now we did discuss the periodic table. And let's not forget the importance of the region of the periodic table. Covalent bonding occurs between elements that are very alike in their electronegativity. Remember that covalent bonding essentially means, and this is the most important feature of covalent bonding for you to realize, is that when you have two atoms that have electrons, neither atom entirely donates the electron. So we'll use our two oxygen atoms, for instance, to talk about bonding. And if we have, here are our two s electrons on each one. I'm not putting the n equals 1 electrons. There are two more electrons at the deeper level, but these are the outer n equals 2 levels, so these are the ones that I'm drawing. So there's two hidden electrons. Oxygen is 8, so it has 8 electrons. And we're only going to show 6 of them on each of these because, like I said, 2 of them are hidden down in the n equals 1 levels. So those don't really interact with anything. So it's only these outer electrons that are starting to interact, which we'll talk more about. But we have then, if each of these has then only 4 more electrons to be able to utilize, right? On that n equals 2 layer, right? But don't forget that this oxygen atom needs 2 more electrons in order to complete its shell all the way up to filled, right? Because we would not want 6, we would want 8, right? And the n equals 2. So in order to do that, this one creates a space for two electrons, and it uses this electron and this electron. This atom creates two spaces for electrons and uses this electron and this electron, and so they share. So this is sort of the way that we imagine them sharing it. There are many more ways to imagine it, more realistic models and so forth, but this is an easier way to think about it, is that the oxygen on the right borrows this purple electron for the purple box, and it borrows the green electron for the green box. Meanwhile, the oxygen on the left borrows the yellow electron for the yellow box and borrows the orange electron for the orange box. So essentially, they are borrowing each other's electrons in order to pretend as though they have eight, so that they don't always have eight, but at least they do sometimes. Um, it's a little bit like custodial parenting. Um, and this is the case for covalent bonding. It means co means that they share, right? Okay. So electronegativity, on the other hand, for electronegativity, remember that we had this other version of the periodic table. This is still the periodic table, but it's a version where each element is sort of graphed in its height, so it's three-dimensional here. It's taller according to how electronegative it is. Now let's recall what electronegativity is. Electronegativity is the idea that fluorine is very electronegative because it is so close to getting its shell filled, its 2p shell filled, because it has 5 electrons in that 2p shell, and it needs 6 in order to be complete. It doesn't really have that many electrons, so it really wants to be filled. You can think of it as, how many filled shells do you have? Um, and since fluorine only has the 1s, or the n equals 1 shell filled, it's really excited about getting the n equals 2 shell filled. Both the 2s and the 2p, right? And so it really needs that last electron, and that makes it so that it will grab an electron from somewhere fiercely. And if it does, then of course it would be a negative ion. So basically, electronegativity talks about how negative something will be if it gets its way. So oxygen requires 2 electrons, but it really fiercely wants those 2 electrons. Not as fiercely as fluorine wants its electron, but it certainly does want those 2 electrons. But it has to go about trying to get 2 of them. So um, it's electronegative, but it has an electronegative, uh, um, a smaller electronegativity because it's not as fiercely trying to grab electrons from everything as fluorine, but it's still the second highest on the entire chart. So then we get to like chlorine and nitrogen, which as atoms are both quite electronegative. Now, don't forget that nitrogen molecules and oxygen molecules are not nearly as uh, electronegative as simply just the atom itself, right? But a nitrogen atom, a chlorine atom, those tend to be also very fiercely trying to grab electrons to fill their shells, right? And then it gets down to the other end of the chart where these things are not very electronegative. They're actually, sometimes we even call them electropositive because they have such a low electronegativity that they're willing to give up their electrons. So if they have their way, really they'd become positive because each lithium has an extra electron, sodium has an extra electron on the n equals 3 shell, potassium has an electron on the n equals 4 shell. So they're just willing to dump those, and that makes them tend to be positive when all their shells are happily filled. So that is why electronegative um, atoms tend to be all the way over here. Don't forget that this is also important for our ionic bonding, right? So for ionic bonds, don't forget that typically we're dealing with something that is one atom is very electronegative and the other one is electropositive or has a very low electronegativity on this scale, right? And so that means that one of the atoms has a tendency to donate its electron to the other atom because it doesn't need it. So then in those terms, we always talk about those bonds from left to right, just like the covalent bonds, but it's a little easier to spot what is left and right on an ionic bond. So potassium and bromine would form, if you look at a periodic table, you'll see that potassium is in the group 1, meaning that it has one electron on the outside that makes it want to get rid of that electron so that it can have filled shells. It doesn't necessarily want to get rid of the electron if it's sitting there by itself, but if something wants to take that electron, it's more than willing to give it away. So bromine, on the other hand, is actually missing an electron, right? And so bromine will have a tendency to grab the electron from the potassium. And so once it gets that extra electron, it is negative. And once the potassium loses that extra electron, or that one of its family members, it becomes positive, right? And then they attract each other electrostatically, and that is what the ion bond is all about, right? And so we would call this potassium. Remember, in order to name it, we would call it potassium bromide. Now, I do not believe in memorizing the chemical table. I know that chemists have to do that because they spend a lot of time making very quick calculations. But I have never memorized the periodic table, and I certainly would not demand that you do so. Um, it's always available to you there. So, I mean, just look at the periodic table and get a sense of what's going to happen based off of staring at it and understanding what we've gone over, right? So you don't have to remember that K is potassium. You can just look at the periodic table and see that. Um, but where it is on the table is important because this is in group 1 and this is in group, oops, well, that's okay, I can just do this. Group 7, right? And so, doesn't look right. So bromine, this is bromine, right? We call it bromide because it's part of a molecule. But bromine is then very, very close to the noble gases. So that's why we said that it gets that negative charge, right? Now, when we call it potassium bromide, what we've done is we've connected these two together and stated that they are one single molecule. The valence electrons are important because valence electrons essentially are the unhappiness that we talked about previously in atoms. So valence electrons are the electrons on the outside of the atom that have a tendency to interact with other atoms. To count these, we would have to count all of the atoms in the last shell that remains unfilled. I think technically the noble gases have um, they have filled shells and they still are considered as having valence electrons, but really from my point of view, they don't have any valence electrons at all. It's only groups 1A through 7A that have the valence. Let's go back to our periodic table here. We had remember this is 1A and 2A, and this is 3A, 4A, 5A, 6A, 7A. These are the ones that generally have the valence electrons, and they can have up to 7 valence electrons. So basically, if you look at these, not in these numbers here, but in terms of um, group A, and then forget about group B here. Remember, this is group B. But if you just consider group A, 1, 2, 3, 4, 5, 6, 7, that group will tell you how many valence electrons it has. So as our example here, we have oxygen. So we have oxygen up here at 8, right? Meaning that it has 1, 2 in the 1s shell. And then it's going to have 1, 2, 3, 4, 5, 6 in its 2, n equals 2 shell, right? So 2 of them are in the n equals 2s, and 4 of them are in the n equals 2, and then the p shell, right, subshell. So again, let's go back and look at how we would write that out. That is for oxygen 1s2. That is these two. And then 2s2. That is, there is nothing over here, so we would need to skip down to the next one. There's 2 more. That's 2s2. And then we count the next one, which will be 2p. There's 1. We'll put 1 and then change that to 2, and then change that to 3, and then change that to 4. So we get, for oxygen, this as the electron configuration. So you look at the last number, right, and that is 2s or 2s2 2p4. The last number is in other words 2, right? So because we have these as the outer shell, not subshell, but the outer shell, then that means that that oxygen has 6 valence electrons. Okay. Now there are some times when people refer to this in chemistry as having 4 valence electrons, but technically it has 6 valence electrons. So you can think of it as, again, just to reiterate, this is the first group on the A region of the chart, and this is the second group on the A region of the chart, the third, the fourth, the fifth, and the sixth. Therefore, the group in the A group, 6A, gives you also the same as what ends up being the valence according to our electron configuration, right? Okay. Chapter 10. Let's move on to Chapter 10. Okay, so Chapter 10 was basically the only thing I really wanted you to get a sense of out of Chapter 10, although there's plenty of great information in there. The number one thing is understanding how to take things from the atomic level to the large level, so that we are basically counting up large numbers of atoms all at once. If you figure out the atomic mass of a particular isotope, then you'll have essentially the number of grams in a single mole of that substance. So let's take a look at our previous, at the periodic table again, and we'll select out potassium. So potassium has an atomic mass of about 39, which we can look it up, but potassium 39 has, of course, a mass of about 39. So we'll look at potassium 39 and find out exactly what its mass is. And if you have pure potassium at potassium 39, and its its atomic number is 19, so we'll put that there. Then you should be able to tell that this thing has 19 protons and 20 neutrons. But anyway, if we look up the mass, we find it is 39.0983 atomic units of mass. This means that if I measure out .0983 grams of potassium, I take this potassium 39 and I measure out that many grams of it, I will have, in whatever bucket I've put them in, I will have this many potassium atoms. That's the definition of a mole, and it's the definition of Avogadro's number. Avogadro's number is the number of atoms in a single mole of a substance, or the number of molecules in a single mole of a molecular substance. So these really are the same term, so I'm not separating these according to slide. Okay, chapter 11, we talked about solutions, and so one of the things we talked about was an acid. Acids, don't forget, they do have features that you can sort of get a sense of um, just by pouring it on something. And so one feature of acids is that they taste a little bit sour, or sometimes very, very sour. They have a tendency to break down metals. You probably don't want to pour them on aluminum foil. I've done this before and it forms dangerous gases, but I did it under very controlled circumstances in a vent hood. So don't do it in your own home. But if you were to pour an acid onto metal, then it would start to basically tear apart the metal at the atomic level, and dissolve that metal into the acid solution. So, and it also releases a lot of hydrogen gas. So, okay. Acids, remember, the key feature here is that they release protons into the solution. And I put H plus here because don't forget, an ionized hydrogen atom is the same thing as a proton, right? So we also call those proton donors because um, they actually donate protons to the solution itself, right? Bases, on the other hand, have also some characteristics about them. They tend to be a little bit slippery. So, if you hold a base in your hand, like ammonia or something, is actually, if you try to rub it between your fingers, is quite slidey. They are not less caustic necessarily. Potassium hydroxide is one of the strongest bases out there. Lye, essentially, that is lye, which they use to make soaps. If you've ever seen the movie Fight Club, that's essentially what he uses to burn the person's arm. It's extremely caustic. It does not make it safe that it's a base, right? Bases can also seriously damage tissue if they're very strong bases. Most substances don't fall under the very strong acid or very strong base category. They're mostly within the reasonable acids and bases category. We also had, don't forget, our pH scale. And on the pH scale, that 7 is considered completely neutral. And so bases go from 8 to 14 and acids go down from 6 to 0. Remember that those have to do with bases are essentially defined by the increase in hydroxide ions in the solution. And acids are essentially defined by how much protons they've added to the solution. But we're actually going to discuss what they call it in your book in just a second. Also, don't forget that this is not a linear scale. So if something is a 4 on this scale and there is a 3 on the scale as well, so two substances, one of them is 4 and one of them is 3, then this is logarithmic, so it means that the substance that's a 3 is actually 10 times, roughly 10 times as acidic as the substance that is a 4. By the same token, something that is a 10 and something that is 11, the 11 is 10 times more basic than the item that's a 10. And so make sure that that's not confusing. We can go up here and say the same thing is true here for a 12 and a 13. The substance that measures as 13 on the pH scale is 10 times more basic than the substance that measures as 12. Okay. For solutions, don't forget that forming a solution is actually a chemical reaction. So it takes two pieces. It takes a solvent and a solute. And so the solvent uh, is the feature of solutions of which there is more. So if you were to put like alcohol and water into a solution, then alcohol, if you have low alcohol and a lot of water, then water is the solvent. If you have a low water content and a large alcohol content, then alcohol is the solvent in that case. So um, together these two form the solution. Okay. Um, you can also talk about concentrations, and I think that's going to be a good thing to to read about in your book, but we're definitely not going to be calculating any concentrations. But just how much solute is in the solvent defines the concentration. So if you have a touch of hydrochloric acid in your water, then you have a very low concentration of hydrochloric acid in the water. But if you put a lot of hydrochloric acid in your water, then you can have a very high concentration of hydrochloric solution. Electrolyte. Now, this is a term that we didn't specifically mention in the videos, but essentially, when you have an acid, don't forget that the acid, uh, it allows protons, it allows ions into the solution, right? If you have a base, well, that is also something that produces ions in a solution. And then also, if you dissolve salts in a solution, well, those also have ions in them. So whenever you dissolve something in a solution that actually releases ions, then you have electrolytes. This is, if I can make a video on this, I will. But this is what actually creates the conductivity in solutions. So when they say it has electrolytes, that doesn't mean very much. Okay, so hydronium ion. Now this is something that we did talk about, although I didn't say these words. So I noticed that in your book, when they have a different way of talking about it than I did. It's not that hard for us to make the connection between the two. I said that acids have a tendency to release protons into the solution, right? There's little hydrogen ions, right? Just little protons, right? What they actually do after you release them is they connect to other water molecules. So if you have an oxygen here and two hydrogens, then what this proton will try to do is it will go over here and be like, hey guys, can I be your friend, right? And so it will actually end up being uh, hydronium. Hydronium is H3O instead of H2O, and it has a positive charge because that proton did not bring an electron to the party, right? So it's really the same idea as loose protons running around, but in reality, those protons won't last long as individual items. They actually have a tendency to cling to the water molecules, however, not very tightly, so they can actually run from one uh, hydronium atom to another. This is kind of cool, actually, so I'm going to go ahead and mention it. So if you have this hydrogen here, if there is something that's like a electric field in the substance that causes that thing to want to travel, then it can actually do hopping, like so. And so this actually is what allows this acid to be conductive. So this completes all of our terms for chapters 9, 10, and 11. There's a lot of really cool information in there. I urge you to look through it. Ask me any questions that you have about the material in those chapters. We are not going to go into a lot of calculation depth on this particular set of chapters. Okay, I will see you guys in our session.